Okay. So you've got the first homework assignment, and that's due a week from Friday. Let's see. And remote students, I posted it on Blackboard, hopefully though, but also I've emailed a copy to your instructors there, so they perhaps can also print a copy out. But one way or the other, you can get a copy and get it onto, oh my goodness, and get it from Blackboard. Well, welcome. Here's the present. Remind me to give you the syllabus too, all right? All right, we're finish up the first section here, just a couple of things. We're talking about three-dimensional space, R3. So the next thing is this distance formula. And this is just measuring the distance between any 2 points in R3. So let me give that to you. It's just an extension of the Pythagorean theorem. So the distance, and we can denote distance usually using the absolute value signs there, from point P1 to point P2, between P1, and then we'll put P1 as X1, Y1, and Z1, and P2 is X2, Y2, and Z2, is, well, it's just the Pythagorean theorem with one more component on it. So it's the difference between the x's, X2 minus X1, and we square that, plus the difference between the y's, Y2 minus Y1, and we square that, and then the distance between the z's, Z2 minus Z1, and we square that, and then we do a square root of the entire thing. Okay. So let's just do one example just to illustrate this. Find the distance between, let's say, the point 2 minus 1 and 7, and 1 minus 3 and 5. Okay. So the distance then is going to equal, we're going to have a big radical square root there. Okay, difference in the x's, 2 minus 1, and we're going to square that, plus the difference in the y's, minus 1, and then be careful, we're going to have a double negative with a minus minus 3, so I'm just going to convert that right off the bat to a plus, and we square that, and then the difference in the z's, z minus 5, and we square that. Okay, so what do we get here? 2 minus 1 is 1, so 1 squared is 1. 3 minus 1 is 2, 2 squared is 4, and 7 minus 5 is 2, 2 squared is 4, so we end up with, what, the square root of 9. Well, isn't that convenient? And that's a 3. So that's just one example of getting the distance between 2 points in R3. What do we got here? Can you please share? Okay, I don't quite understand that. Oh, because it's behind. Sorry. Can you see that now? No. Oh. Oh, I'm sorry. I am terribly sorry. Okay. All right, let me just keep that up there on the screen. Let me just, sorry, beginning of the semester stuff. What I had put up there on the screen is the distance formula between 2 points in R3. So let me just leave that up there for a minute so you guys can copy that down. All right. it'll take me a couple of classes to get back in the technical mode of things where I just don't deal with you guys, I deal with those guys too. Okay, can you pretty much got that copied down? And then I just went through an example of that. All right. Okay. All right, and whoops, where are we here? And then one other concept here from this section has to do with the equation of a sphere in R3, of course. We remember that the equation of a circle in R2 is x minus h squared plus y minus k squared equals r squared, where the center is h comma k of the circle, and r is the radius of the circle. All right? Okay, so now we're going to expand that into R3, where we're going to be talking about a sphere. One thing I do want to point out before I go to R3 is this, just as a reminder for you folks. The center here, the coordinates of the center, are going to have the opposite sign of the numbers that you have there in the parentheses. Okay, just so that you remember that. Okay, so let's then go to the equation of a sphere. In R3, and we're going to say the sphere has the center. Well, we need 3 coordinates, so it's going to be h, k, and l. And let's give it, and a sphere also has a radius. Let's again have it the radius r. The equation is this. It's just the extension of the circle, x minus h quantity squared plus y minus k quantity squared, and then this is our z coordinate, z minus l quantity squared equals r squared. All right, so that's the equation of a sphere. An example I want to go over with this involves completing the square. When you had algebra, you had similar kinds of things with completing the square in algebra. So let's look at this. Example, we want to show that this equation here, x squared plus y squared plus z squared, and then we've got these other terms, plus 4x minus 6y plus 2z plus 6 equal to 0. I want to show that this is the equation of a sphere. Show that this is the equation of a sphere, and we want to find its center and radius. All right. So what we have to do with this is we have to complete the square for x, for y, and for z. So complete the square for x, y, and z. And another thing that we want to do right away is we want to get this 6, plain old 6, moved over to the other side of the equation. So let's just kind of bunch all the x stuff together. So we have x squared plus 4x, and let me leave a space. Then we have y squared minus 6y, and let me leave a space. Then we have z squared plus 2z, and I'll leave a space. And then I'm going to move that 6 over, so that'll be a negative 6 on the other side. Okay, so we have 3 variables there. We want to complete the square. So do we remember the process on completing the square? Right. Divide the coefficient by 2 and then square it. This is assuming, of course, that our coefficient of the square terms is a 1, which very conveniently it is here, okay? So we take the 4, divide it by 2, and then we square that. So that gives us a 4. So this is going to be x squared plus 4x plus 4. And we all know from algebra what we do on one side, we got to do on the other side. So please don't forget to add the 4 over on the right side. We do the same thing here. We take the minus 6, we divide by 2. That gives us a negative 3, and we square that. And that gives us a 9. So then we have plus y squared minus 6y plus 9. And so since we're adding on a 9 there, we better add a 9 over on the other side. And then finally with the z, we have a 2z. 2 divided by 2 is 1. 1 squared, of course, is 1. So that's z squared plus 2z plus 1. And then we have to add that other 1 over there. So what we end up getting with this then is 3 perfect squares in x, y, and z. The first one is going to be x plus 2. This number that we got when we divided the coefficient by 2, that is what we put next to the x in the parentheses, and then we square the whole thing. Plus, now y, we got a negative 3 when we divided by 2, so it's going to be y minus 3 in parentheses squared. And then we got a 1 when we divided the 2 by 2, so that'll be z plus 1, parentheses squared. And then we combine all the numbers that we had there. That's 14 minus 6, so we end up with an 8 over on the other side. Okay, so now we can basically read off our radius and center. This is r squared, so the radius is the square root of h, which is, we could also simplify to 2 times the square root of 2. Okay, the center, now remember, we have to do, whatever number we have there, we have to do the opposite sign for the center. So our x-coordinate is going to be a negative 2, y-coordinate is going to be a plus 3, the z-coordinate will be a minus 1. And then that's our center. Okay? All right. Okay. All right, so that is what we want to cover there in just in that first section. Then the next section we start getting into something a little bit more interesting, I think. We start talking about vectors. And this is a concept that we're going to be using all semester long. So this is section 12.2, and it's an introduction to what vectors are. So if you don't remember, well, I shouldn't say this, but what you need to remember with vectors is that they have 2 things. They have a direction, and they have a magnitude. Okay, so let me put this down. A vector is, I just put, is something, which is pretty vague, that has both magnitude. Now, another word for magnitude is size, and the other component thing it has is a direction. All right. So in the easiest place to look for vectors is in physics. So there's vectors all over the place in physics. Certainly a velocity. A velocity doesn't have both a magnitude, that's how fast you're going. But it also has a direction. Am I heading this way? Am I heading this way? So velocity. And also the next thing up from that is acceleration. Acceleration has a magnitude and accelerating in a direction. So acceleration. Also, A displacement vector, that's a change in your position. That has a magnitude and a direction also, and that's called a displacement vector. And then another important one in physics is force. Force has a magnitude, and force is exerted in a certain direction, right? Okay. Now, just for how we denote vectors, we use arrows to denote vectors. Well, there are a couple different ways that we can denote vectors, but one way is using arrows. And basically, the length of the arrow denotes the size of the vector. The length denotes its size. And then the direction that the arrow is pointed denotes its direction. And the arrow points in the direction. All right. Okay. So therefore, we have here. These, for those of you, this is the first class. This is like a 3D graphing where you have X, Y, and Z, and I made these a little bit darker, so those other lines do show up a little bit better than the other day. But anyway, a vector. We can start here to here. That's a vector. It's got a certain magnitude. It's got a certain direction. So vectors like this, they can go all kinds of different ways. But that's, as far as geometrically, that's the kind of thing that you think of with vectors. Also, just for notation purposes, for vectors, we either write them in boldface or with a little arrow on the top of them. So another thing that's important to remember is this. We denote vectors either using boldface or, and this is going to be more common for me, by putting an arrow over the letter. Putting an arrow above the letter. Okay. So let's just say something like, say we have a particle that moves from point A to point B. That'll give us a displacement vector. So here we have point A in three-dimensional space. Here we have point B. The particle's moving from A to B. So we show the length of that shows its magnitude. The arrow shows that it's going from A to B, all right? So this would be considered a displacement vector. And we could denote that, there's a couple of ways we can denote it. We can denote this as putting, okay, here's our first point, here's our terminal point, and then we could put an arrow above it like that. That's one way to denote it. Another way is just to say, okay, I'm going to call this thing vector V, small v, and let me put a little arrow over the V. All right. So we can denote it like that. Some terminology here. This point where the vector starts at is called, we can call that its initial point, or we can also call that like its tail. Then this point up here where the vector stops, we can call that its terminal point, or alternately its tip. Okay. Now, vectors just have size and direction. So if the size of two vectors and their direction are equal, then the vectors are equal. Okay? So let's just put this down here. Two vectors are let me put that in quotes, equal, or I could also say that they're equivalent if they have the same length, and the same direction. Okay. Now, what's crucial here about vectors is this. These two vectors don't have to start at the same point in three-dimensional space to be considered basically the same vector. And that's something that you need to understand about vectors. So let's just do a little quick, here's my x, pointing out to me, here's my y, here's my z. Okay, so I could have one vector like this. Let me call this little v. Okay, it's got a direction, it's got a length. I could have the very same vector up here in space at a different location. We can call that w. Or we could even be over here somewhere, same length, same direction, same vector. And we could call that u. So these are three equal or equivalent vectors, even though they start at three different points. Even though they start at three different locations or points. All right. And so we can say, all right, u with an arrow over it equals v with an arrow over it, and that in turn also equals w with an arrow over it. Okay, they're all equal to each other. Now we can do a lot of operations with vectors. The first thing we can look at is we can add two vectors together. And we're going to learn two different ways we can do that. The first is kind of a geometric way. The second way is going to be an algebraic way. All right. So let's adding two vectors. So this is going to be the, shall we say, the geometric way. All right. So basically, if u with an arrow, u and v with an arrow are vectors in space. And when we talk about space here, we're talking about three dimensions. And they're positioned so that the tip of u is at the initial point of v, and they're positioned so that the tip of u is on the initial or tail, initial point of v. So let's just draw this here. So we've got u like this. And then we've got, okay, here is the tip of u, and then starting at the tip of u, we have v starting there. So the tail of v, or is at the, or the initial point of v is on the tip of u. All right, we can then say, then the sum of these two, u plus v, is the vector that starts at the initial point of u and ends at the terminal point of v. Is the vector that starts at the initial point of u and ends at the tip or terminal point of V. So basically like this, adding these two together, we just started our initial point of the one and at the terminal point of the other. Okay? This is geometrically. And so this vector right here is U plus V, adding the two together. All right. Now, so we had U and V, and we added U, and then to U we added V. Well, we could have just as well gone the other direction here. So I want to point out here is note that U plus V is going to be equal to V plus U. All right. So let's look at that. So let's draw again. Here's U. And then we're adding on to that V, so I'm starting V right there. That's what I had drawn previously. Now let's look at V plus U. So with V plus U, unfortunately, different colors don't show up on this thing, which I wish it did. So with V plus U, let me start with V. And then from the tip of V, let me add on U. And we're going to come to the same point. And the vector that we get is the same for both of them. This diagonal that we see, this thing is actually called a parallelogram. Parallelogram. But the two opposing sides are parallel to each other. The diagonal is the sum, is equal to the diagonal. And so this diagonal here is both V plus U, or the other way around, U plus V. So they're both equal to each other. All right. And again, don't feel that U plus V has to be stuck in this one spot in space. So basically, X, Y, Z, let's see, U plus V kind of looked like this. Or we could also have said this is V plus U. But it's not stuck in that space. As long as we have the same length and the same direction, we could just as well put that same vector. Let's see if I can kind of draw something that looks the same as that. It's, a little bit off. This could also be U plus V. Same direction, same length. Okay. All right. Another thing we can do with vectors, besides adding them together, is we can multiply a vector by a number. And in this case, for terminology purposes, we call a plain old number, we call it a scalar, all right? So we can also multiply a vector by a real number, any real number. Let's call the real number small c. And again, this can be called a scalar. So become accustomed to that terminology also. All right, so let's look again. Right now we're just looking at geometrically. We're going to look at algebraically in just a couple minutes. But geometrically, this is what happens. Multiplying this scalar by a vector, so we have c, some number c times our vector, it points in the same direction as our vector, in the same direction as v, if C is a positive number, if our scalar is a positive number. However, we can multiply a vector by a negative number, in which case it'll point 180 degrees opposite. So CV points in the opposite direction. If C is a negative number. All right. Now, we have a new vector now, C times V. The length of that new vector is the length of the original vector times the absolute value of the scalar. So the length, so this one here, these talked about direction. The length of C times V equals the length of, well, let me just do, the length, I'll write it out, the length of our original vector times the absolute value of C. Okay. Because length we don't think of negative length. We always think of length as being a positive number. So let's just draw a couple of pictures here. So if this is our initial vector V, minus V, which is really minus 1 times V, or minus V, it has the same length, but it's pointed in the opposite direction. All right? Now, say we multiplied our original vector by 2, we would have the same direction, but it would be 2 times the length. So here is 2 times V. And if we multiplied it by negative 2, it would have twice the length, but it would be going in the other direction. So we change direction. All right. And of course, we can multiply vectors by fractions. So if we had, so something maybe like this would be 1/2 times V. It would have half the length, same direction, but minus 1/2 times V, half the length, but we would have it in the opposite direction. Okay. An important point, so for those of you who are new, a lot of times I'll put things I want to emphasize, I'll put a little asterisk or something by it. Also, for those of you who are just here for the first time today, ample time prior to the first test, I'll again be providing you with a practice sheet with some information on it, some problems on it, and that'll have some stuff that you perhaps might want to know. All right. Okay. Let's put asterisks here, and this is the fact I want you guys to remember. 2 vectors are parallel if they are scalar multiples of one another. If they are scalar multiples of one another. So if we just take a vector and multiply it by any kind of number other than 0, all right, 0 just as a dot, all right, then we're going to have 2 vectors that are parallel. So basically, all of these vectors up here that I drew, they're all parallel to each other, all right, which means they're going in the same direction. Just like railroad tracks are parallel, hopefully. Right. Okay. Since we can talk about what a minus V is, which is minus 1 times the vector, we can also now subtract 2 vectors. So we can also subtract 2 vectors. And basically, okay, so what does it mean here? Let's take a vector u and say we're subtracting from it the vector v. Well, what this really means is we're taking the vector u and we're adding to it the -1 vector, -1 times the v vector. That's really what we're doing. So here, if we, again, this is all geometric. We're getting to algebra in just a minute. So say we have u like this, and say we have v like this, and say we want to represent u minus v. Well, okay. Well, if v is like this, then in the opposite direction is going to be minus v, right? Opposite direction. So u minus v then is going to be u plus minus v, like this. Let's see if I can, minus v. And then we just join, and this is from going from the head of the u to the tail of the minus v, like we had done before. And then we just look at the vector we get from the tail of the first one to the head of the second one. And then this then is my u minus v right there. U plus minus v. Okay. Any question on that? Have you guys been introduced to vectors before? So it's like, this is, for many of you, this is old hat, or sort of. Okay. So I'm usually a pretty terrible drawer. So I'm always relieved that something can be done algebraically. Thank the Lord for algebra. So vectors can also be represented algebraically rather than drawing all these little pictures that I'm so bad at. So we can treat vectors algebraically. Yay! Treat algebraically. All right, so therefore what we do here is, these are all, we're talking about three-dimensional space, so a vector is going to have three number components to it. And when we draw points or represent points in space, the convention is to use parentheses. So we need something to say, well, wait a minute, this isn't a point in space, it's really a vector. So what can we do? We have to use a different kind of notation on our paper. So we're going to use what are called angle brackets, like this. Brackets with our three number components, A, B, C, in them. So this represents a vector in 3D, three-dimensional. Okay, so what does this A, B, and C mean? Well, we know vectors have directions. So this represents a vector that goes, here's our A here. It goes A units in the X direction. Now, A could also be a negative number. B units in the Y direction. B units in the Y direction. And then finally, C units in the Z direction. And C units in the Z direction. We'll talk about magnitude in just a few minutes, but this is, first of all, just looking at the direction of this thing. These numbers here have a name, and they're called components. These numbers are called components. So either call these brackets or angle brackets, whatever you want to, but that's the name for them. So let's look at something here. Let me get out some my 3D stuff, graph paper here. And let's look at this vector here, -3, 2, and -4. All right. Okay, now in fact, now this is, for those of you who weren't here, that this is the x, this is the positive x direction, that's the negative x direction. This is the positive y direction, that's the negative. This is the positive z direction, that's the negative z direction. All right. And maybe even just to kind of emphasize that a vector isn't tied to any one place in space, let's just start out maybe here. Now, what does this say here? It says we go -3 in the x direction. The x is on the line this way. If I'm going to go a -3, that means I got to go in this direction. So that's 1, 2, 3. Okay, let me put a little bigger circle there for the tail. So -3 in the x direction. Then I'm going to go 2 units in the positive, this will be the positive y direction. Positive y direction is going down like this. So 1, 2, like that. And then finally it's going to go -4 units in the z direction. So that's going to be downward vertical, 1, 2, 3, 4. So actually this vector then would look like that, okay? All right. And then, of course, this very same vector could also be anywhere else here. Like here, it could also be here, or anywhere else in 3D space, all right? So that's what those 3 components mean. Now, with algebra, it's really easy to add and subtract vectors. We just add or subtract the components, all right? So that's easy. Add or subtract the components. All right, so let's just do one example here. 2 -7, 10 -3 -2, and 4. Okay, let's see what those equal. Now we are subtracting here, so I'm going to be subtracting the individual components. So this is going to be 2 -3. That'll be the first component. Again, always watch out for your double negatives. This is going to be -7, but I've got 2 minuses, so it'll be a +2, and then it'll be 10 -4. So simplify, that becomes 2 -3 is -1, -7 + 2 is -5, 10 -4 is 6. So it's just that simple. All right. And then also we can multiply a vector by a scalar. And to do that, we just multiply all 3 components by that same scalar. So when we multiply a vector by a scalar, we multiply all 3 components by that scalar. Okay, so that's pretty easy also. So we'll just do example here. Let's take -3, and we're multiplying the vector 2 -5 -7. And all we do is just multiply each component by the -3. So that's, again, is -3 times 2 is -6. Minus 3 times minus 5 is a plus 15. Minus 3 times minus 7 is a plus 21. Okay. What can we say about this vector here? Let's call this vector v sub 2. Let's call our original vector, say, v sub 1. What's one thing we can say about v1 and v2? Besides the fact that they're vectors. They're parallel, right. So, these two vectors are parallel to each other because they're just scalar multiples of each other. Okay, so big note here, that 2 minus 5 minus 7 is parallel. And sometimes you might see this notation looks like two railroad tracks parallel to minus 6, 15, and 21. They have the same direction. Okay. Different magnitude, but same direction. All right. For those of you who are new, don't worry that I'm going to go nonstop until 10 to 12. We will take a 5-minute break around 11 o'clock. All right. So if you were starting to freak out about that, we will take a little break. If we have 2 points in space, yes, Jenna?
You said if they're in the same direction, but are they on opposites because they're multiplied by a negative?
You're right. They are going in opposite directions. Very good. They're still parallel. You can be parallel of going in one direction and going in the other. But yes, absolutely. Score 1 for Jenna. If we're given 2 points in space, actually 2 points in space can, in a way, generate a vector. It can generate a displacement from point A to point B. So let's just get this down here. So say we're given 2 points, and frequently this is how you're going to see. You might see the point denoted with, say, a capital letter, and then after it you're going to have some numbers. Here I'm just going to put A1, A2, and A3. So this is point A. And then we have, say, a point B. So we have capital B, but then we have B1, B2, and B3 in space. And notice these points, we have parentheses here for the points, not the brackets. Then the displacement vector starting, say, at A, going to B with an arrow over it. Okay, we can represent this algebraically also. It's going to be, it's starting at A, ending at B, so we're going to take the components of B and subtract from them the components of A. So the first component is going to be B1 minus A1, second component B2 minus A2, third component B3 minus A3. And they'll be in those angled brackets. Here A is the initial point, and B is our terminal point. Terminal point. All right. And so what we have here then, it's basically terminal components minus the initial components. Terminal components minus initial components. Okay, alrighty. So I'll do one simple example here. So say we're given that point A is equal to 7 minus 4 and 2. Again, I'm using parentheses there. And point B is equal to 3, 2, 1, again using parentheses. Then A, B, starting at A, ending at B, that vector is, now here I'm going to be using the brackets, because I'm talking about a vector now. Okay, it's going to be the A components minus the, it's the B components minus the A components. So that's going to be 3 minus 7, 2 double minus 4, so 2 plus 4, and then 1 minus 2 in the angle brackets. So this, a displacement vector, is what? 3 minus 7 is negative 4, 2 and 4 is 6, 1 minus 2 is minus 1. Right. Okay. I think we'll start the 5-minute break now, then we'll finish up. So we'll come back about 2.5 minutes after 11. Feel free to stand up and wake up, or go to the restroom, go to the drinking fountain, whatever. So you decided, or that your work schedule will allow this?
Lack of work schedule allowed it.
Oh. Oh.
Well, that we were really slow. So. Not really.
Yeah.
Yesterday. Those people see that you get hand off. It's very
Worried I might do a grade change or something? Okay, you Eureka people. I put a question out there for you. I haven't. Do you have an answer? Thank you, Annalie. I told Annalie she's got an A in the course already because she answered the question. Annalie, I've also got some land and sell you for a good price too. But thank you for answering. Oh, I guess we better get started here. All right. We're still looking here at these vectors. So, one thing I want to say here is that, usually we denote, we know that the origin here in 3D is, 0, 0, and 0, and we often indicate it with just the letter O. We often indicate it with the letter O. All right. So if we're given any point in three-dimensional space, we actually can, it kind of automatically gives us a vector in a way. So let me put this down. So given any point, we'll call it point P with an X, Y, and Z for its components. Again, this is a point, not a vector. We can call the vector, now we're going from a point to a vector, and this vector is the displacement vector starting at that origin, that point O, going to the point P, all right? And that is going to be, okay, it's going to be X minus 0, Y minus 0, and Z minus 0, right, when we're going from one point to another. So this vector is just our X, Y, and Z coordinates. But it's a vector. We call this vector the position vector of point P. All right. Let's just look here at an example, and then I just want to kind of make sure you understand the differences here. So let's say, suppose we have a point A, 3 minus 5 minus 2. This is a point, fixed point. It's got parentheses around it. Then OA vector is equal to, now we have the angle bracket, 3 minus 5 minus 2. This is we can call this a displacement vector or a position vector. Two words we could use for it. All right, so let me just do this here on the paper rather than looking at doing the graph paper. Here's X, here's Y, and here's Z. Okay, so let's look at where A is. A goes 3 units up with the X, so 1, 2, 3, and then it goes minus 5 in the Y, in the negative Y direction, so we're going to go in this other direction, 1, 2, 3, 4, 5. So we're going to end up here. And then finally we go minus 2 in the Z direction, 1, 2. So we're going to go down 2 like this, down 2, and we're going to end up somewhere like this. So this is our point A. It's stuck there in space. That point doesn't move. But we can call this, and this is our point O, or the origin. So therefore, we can have this vector that seems to start at that origin and goes to the point A, and this would be OA with a arrow above it. This would be our position vector. Now let's say, in order maybe to avoid confusion, let's call V with an arrow over it. Let's call V equal to the OA vector. All right. Remember, vectors are not stuck in space. So even though this vector was kind of determined by a point, this position vector, as long as we have the same size and direction, I can put this anywhere in space. So I could go up here, have something same length, and this could also be my V vector. All right. What I think I really want you to leave you with this thing is the fact that points in space are not the same as vectors. All right. We can get a vector from a point, but remember, vectors can move around. Points are stuck right there where they are. So points in space are not the same as vectors. There can be a relationship, but they're not the same. All right. Now, so far, let's see, we've looked at how we can add and subtract and how these three components give us the direction that the vector is pointing. But we can also algebraically determine the size of the vector. So for magnitude or size, we have this. The length of the vector A, let's say that A is, okay, we've got the angle brackets, A sub 1, A sub 2, A sub 3. The length of this vector equals, okay, one way we can just, in a shorthand way, denote the length of a vector is again with the absolute value signs. Now, what does this actually equal? Okay, it's basically going to be the distance of that point from the origin. So basically, it's going to be the square root of the first component squared plus the second component squared plus the third component squared, all under the square root radical. Okay. So example, if vector A is equal to 4, 0, 3 in brackets, then the length of A, absolute value there around that, is equal to the square root of 4 squared plus 0 squared plus 3 squared squares of all those, and that's going to be the square root of 25. So our length is equal to 5 in this case. Okay. Now, we want to talk about three special vectors that have length equal to 1. So 3, and I'll put this in quotes, special vectors. And I'm going to represent them both algebraically and then we'll see them geometrically. The vector I, with that arrow above it, is equal to 1, 0, 0. So our x is 1 and our two others are 0. J, with an arrow over it, is the vector 0, 1, 0. So the x and z part of it is 0, but the y is 1. And then k, with an arrow over it, is 0, 0, 1 in brackets. So one thing we want to remember, I, J, K, they go along in the alphabet, I, J, K, and the one has a 1 in the first spot, the other one a 1 in the second spot, the third one has a 1 in the third spot. These all have length equal to 1. If we do that length formula, they all have length equal to 1, which means, this is a new term perhaps, I think it is a new term, that these are unit vectors. Unit vectors have length 1. Okay, so their size is 1. And let's look at what these things look like geometrically here. So here's x, y, and z. Okay. The I basically has points only in the x direction. So it's like this. I can try to make that a little bit darker. Okay, I did that. And that would be the I. The J points unit length 1 in the y direction. That's our J. And then our K goes up in the z direction, unit 1, and that upward arrow is the, oops, that's our K. All right. They have a name other than special vectors. These are actually called standard basis vectors. Basis because there's a connection into the field of linear algebra, which we don't talk about here really, but where we talk about bases in a vector space. So these are called standard basis vectors. Okay. The nice thing about these three little vectors is this, is that we can take any vector and represent it as the sum of these three vectors multiplied by a number, all right? Which is why they're called basis vectors. So let's put this back down here, back. Any vector in 3D can be written as a combination of these three standard basis vectors. Of these three standard basis vectors. So let's give an example of how this can happen. Let's just take any kind, let's just get an arbitrary point. I'm just picking here. So example, 4, minus 10, and 2. So that's just like some kind of vector in three-dimensional space. I'm going to do this in a couple of steps. First of all, by the way that we can add vectors together, this can be considered the sum of these three vectors, 4, 0, 0, plus 0, minus 10, and 0, plus 0, 0, and 2. Because if we add these three vectors together, adding their components, we're going to come up with the vector that we started with. So we can do that, but then let's look at these individual ones. This 4, 0, 0 can be written as 4 times 1, 0, 0 by multiplying by 4. The second one with a minus 10 in the middle can be written as minus 10 times 0, 1, 0 by multiplying. And the third one can be written as plus 2 times 0, 0, 1, right? And those three vectors are our standard basis vectors. So these are 4 times I minus 10 times j plus 2 times k. So any vector, you look at this number component, and you can see directly, you can see directly from the vector that we started with how that would be written as a sum or difference of those three. I don't know who knows what they're doing. It's an art class next door, so they got all kinds of stuff in the next door. So do we see how any vector can be written like that? Right? Now, I had already said that a unit vector is a vector whose length is 1. Unit vector is a vector with length 1. So if we have any non-zero vector, we can actually multiply it by something to make it into a corresponding unit vector. So we're going to see this with an example. So if A with an arrow is any, now we're only interested here in non-zero vectors, we can get a corresponding unit vector now. And the way that we do this is we multiply out front by 1 divided by the magnitude of the vector. So the unit vector in this case would be unit equals 1 over the magnitude of the A vector times the A vector. And this is the corresponding unit vector. And I'm going to do an example in just a minute. Or I could write this as the A vector divided by its size. So let's look at a concrete example of this, how we can do this. Example. And this could find the unit vector in the direction of V, and get used to two different ways that you're going to see vectors written. Here I'm going to write my V as this, 2 times the I minus the J minus 2 times the K. That's how I'm going to write it here. An exactly equivalent way of writing that same vector is this, using the angle bracket. 2, this minus here corresponds to minus 1, and then we have minus 2. So these are two different ways of writing the same vector. One using those basis vectors, the other using the angle brackets. Now, actually, I didn't say something previous that I want to say here. going back to this unit vector, notice I took the original vector and multiplied it by 1 over its size. So I multiplied it by a real number. So therefore, this unit vector is parallel to the original vector. And since this is a positive number, it goes in the same direction. The unit vector goes in the same direction. As the original vector, all right? So in this example here, we're talking about a unit vector in the same direction of this vector. We just have to multiply this vector by a certain number to make it into a unit vector. So what we do here is we have to multiply by 1 over the length of the vector to do this. So let's find the length of the vector so that we can do that. The length of the vector v is, okay, the square root of 2 squared plus minus 1 in parentheses squared plus minus 2 in parentheses squared. So let's see what that gives us. That's the square root of 4 plus 1 plus 4. So that's, again, let's see, oh, that's a nice number again. That's the square root of 9. So our length of this vector is 3. So if I multiply this vector then by 1/3, to get the unit vector. Okay, so 1/3, and I could write it 2 different ways. 1/3 times, or actually 3 different ways. I'm going to put a couple steps in here. 1/3 times 2i minus j minus 2k, and that's the same as just distributing 2/3 times the I vector minus 1/3 times the j vector minus 2/3 times the k vector. I'm just distributing. That's one way right here that I can write it using the I, j, and k. And you can certainly, if you want to, you can check by taking the square root of the squares of all those components. You'll come up with a length of 1. Or another way I can write it is just using the angle brackets, 2/3 minus 1/3 minus 2/3. Okay, either way. So know how to get the corresponding unit vector by multiplying by 1 over the magnitude. Okay. This is getting into a little bit of physics stuff here. And so you're going to see that throughout the course. If we have a force, or actually any kind of vector, we can look at its horizontal and vertical components. Say, for simplicity here, we're just looking at 2-dimensional, 2D. We can have a force, or let me put it this way. In 2D, there are horizontal and vertical components of a force. There are horizontal and vertical components of a force. Okay. Let's just look. Now here we're just looking at 2D, so here's y and here's x. And let's put the force vector. So remember, vectors have a magnitude and a direction. So let's say this force vector is going off like this, and it has an angle to the of alpha to the x-axis. Now, the length of this vector would be the absolute value of the force vector. That would be the length of it. Okay. Now, we can then represent this force vector F as the sum of its horizontal and vertical components. As the sum of its horizontal and, oops, I forgot a word here. Horizontal and vertical components. And this is just using some trigonometry, our favorite topic. Let's just drop a dotted line down here at a right angle and make it go down to the x-axis. The length of this part here is going to be that absolute value times the cosine of the angle. So the length of this one is the absolute value times the cosine of theta. And the length of this part here is again going to be the length of our hypotenuse, which is the absolute value of the force, times the sine of theta. All right? And then this is going in the x direction, so we've got that unit vector I that goes in the x direction. And here we've got that unit vector j that goes in the y direction. We don't have a z because we're only talking about x and y. So I can represent this force as the sum of this vector plus this vector right here. Adding those two vectors together, we will get the diagonal vector. So we can say this, that our force vector is equal to, okay, what's the magnitude of our horizontal? Well, it's the magnitude of the force vector times the cosine of the angle. That's the length in the x direction, but we need to multiply that by that unit vector in the x direction. And then we get the vertical component. Again, that's going to be the size of the vector. Now it's times the sine of alpha, and that'll be multiplying my vertical unit vector, the j. And that way I've broken up our force into two components, the horizontal and the vertical, all from knowing this angle that it makes with the horizontal. You okay with that? All right? Another way I can write this force, I could use our bracket notation. Actually, there's a couple ways I can do this. Our x component is going to be the absolute value of the force times the cosine. Our y component, the same thing except times the sine. And another thing I could do, since both of them have the same absolute value in them, I could draw that out and write it as the absolute value of that force times bracket the cosine of alpha, sine of alpha, like that. Okay. So I want to just do a problem here with this, and then I want to do another problem that you don't have in the homework, but I think it's kind of interesting, especially if anybody is going to go into engineering or physics. All right. But here, let's do this one example here. All right. So say we're pulling a cart along, and we're pulling it with a force of what's called 20 newtons. Pulling a cart with a force of 20 newtons, capital N. Let me do a basic aside here before I go any further. Force in physics is the mass times the acceleration. Okay, that's one of Newton's laws there. If our mass is measured in kilograms and our acceleration is measured in meters per second squared, so if we have those dimensions for mass and acceleration, then our force is in newtons, capital N. So anyway, this is our force, and we're pulling this cart at an angle of 60 degrees. At an angle of 60 degrees from the horizontal. Okay, so it's just like some little kid with a wagon or something like that. All right, we've got our cart here. We've got our handle here. This handle here has an angle of 60 degrees from the horizontal, and we're pulling this cart along. All right. Basically, what we want to do here is represent the force using the horizontal and vertical components. Using the horizontal and the vertical components. Okay, so basically here, this along the so let's just kind of abstract this here. And here's our angle here of 60 degrees from the horizontal. And we know that the force here has a magnitude of 20 newtons. All right? So that's our force vector going up at an angle. And basically, we want to get the horizontal and the vertical components there of that, and we just use the sine and cosine to do that. So therefore, the size of the horizontal component is going to be 20 newtons times the cosine of 60 degrees, and the vertical component is going to be 20 newtons times the sine of 60 degrees. And let's see, the cosine of 60 degrees is 1/2. So this is 20 times 1/2, which is equal to 10. And the sine of 60 degrees is square root of 3 over 2. So this is going to be 20 times the square root of 3 over 2, which simplifies to 10 times the square root of 3. So those are the sizes of the horizontal and vertical components. So I can write here that our force, breaking it up into the horizontal and vertical, is 10, that's the magnitude in the horizontal, times the I unit vector, the horizontal one, plus 10 times the square root of 3 times the vertical unit vector, J, just breaking it up. Right. What I want to look at here, and we have some time left, and I thought I would, I usually don't go off the beaten path, but I think I will for this thing here, because it's an interesting example, and I know some of you will be going into engineering or physics, and so I think it would be a nice thing to look at. This is actually one of the problems in the back of the section, and this is problem number 36. It's on page 823. I don't have these for homework for you guys. It would make it, some of these could have done these like extra credit type of homework things. But anyway, this thing is, we've got this star there. You see how good my drawing is. That's some kind of Christmas ornament. And this it's a heavy Christmas ornament because it weighs 5 kilograms. Which I think is a little bit over 10 pounds. It's like 12 pounds or something, isn't it? Kilograms, about 2.2 pounds. Am I right on that? Anyway, we got this big, heavy star, and it's affixed with these, I guess, string or wire, probably, to 2 horizontal surfaces that are not even at the same level. One here is lower down than the other one is. One of these wires, this wire is 5 meters long. Oh, wow, meters. So this must be something out of a department store or something like that. This wire here is 3 meters long. And we have angles. We know the angles that these wires make with the horizontal beams, I guess. This one makes an angle of 52 degrees, this one an angle of 40 degrees. And what we're asked to find is the tension in each wire and the magnitude of the tension. Okay. So when you look at something like this, what you have to look at are what are the total forces that are acting on this star that's just able to stay there still in space. Because we know that one force that's acting on all of it is gravity, which is a vertical force. So what we have going on this star is this. We've got gravity going down, and then we have this, what do we call this? Tension going this way, and we've got a tension going this way, and those are all equaling each other so that this thing doesn't move, all right? Now, I put 5 and 3, put the subscripts for 3 meters and 5 meters. Those are the tensions. All right, now gravity, all right, we know is the mass times the gravitational acceleration. Force is magnitude times acceleration. Here we're told that it is 5 kilograms. And the gravitational acceleration, one way to represent it is this. It's 9.8 meters per second squared. All right. So if I multiply these two numbers together, I get 49, and my dimensions are actually kilogram meters per second squared. All right. So that's the force going down. So basically what I can say is that vertical force going down is equal to 49. All right. Now, what we have here is we can take these two forces that these wires are exerting, and we can break them up into their vertical and horizontal components. So I can take this one, and I can take this one and break it up. We're given the angles here. This angle here is 40 degrees. This angle here is 52 degrees. All right? So we can end up getting a couple of equations here from this. First of all, the vertical forces have to balance each other out. So let's look at the vertical forces on this thing. Okay. We've got the forces going up from the two wires. So because we're looking here, we have to look at the sine of the angle because we're looking at the opposite side. All right. We don't yet know what this magnitude of this tension is. So I'm going to say this. We have the magnitude of T5, whatever that tension is. This length here is magnitude of T5. This length here is magnitude of T3. T5 times the sine of 40 degrees, plus, now we've got the other one, also the vertical component of that, magnitude of T3 times, now this time it's the sine of 52 degrees. So those are going up. The downward thing is the 49 gravity. So that's one of our equations. Then we have to look at the horizontal components. This thing is staying in one position. So the two horizontal forces are going to be equaling each other. So the horizontal forces, and this is probably a really simple problem whenever you take statics. This would probably be one of the beginning problems in that kind of a course. Okay, the horizontal force for this one, let's call this the negative direction this way. So we're going to have here minus the magnitude of T3. Now this time it's going to be the cosine of the 52 degrees plus the magnitude of the T5 in the positive direction times the cosine of 40 degrees. These two balance each other out, so they're going to end up equaling 0. Okay. So what we have here then is we have two equations in two unknowns. The unknowns here are the magnitude of the T5 and the magnitude of the T3. Let me actually write this second one a little bit differently here. All I'm doing is going to flip these. I'm going to write the second one as the magnitude of T5 times the cosine of 40 degrees. I'm just changing their location here, minus the magnitude of T3 times the cosine of 52 equals 0. There's a reason I'm going to do that. Okay, so we have two equations and two unknowns, and I'm going to choose to solve it using Kramer's rule. All right, so we have this one here, and we have this one here, and let's remember Kramer's rule with this. All right, so let's see, let's go with T5. Now with this one, what we do with Kramer's rule is this. We have a determinant on the top and we have a determinant on the bottom. The determinant on the top, for the T5, we put the numbers that we have on the other side of the equal sign, so that's 49 and 0, in our first column. In the second column, we put our coefficients from the other variable, which is the sine of 52 degrees. That's that coefficient. And careful with this one, this is negative cosine of 52. All right. We figure that determinant. On the bottom, then, we do the determinant of the coefficient, so that's sine of 40. Then here it's cosine of 40, sine of 52, cosine of 52. All right. Oh, sorry, negative cosine of 52. All right, this is Kramer's rule. Kramer's rule is this. If you have, say, let's just look at a system of two equations and two unknowns. Let's look at AX plus BY equals C, and DX plus EY equals, F. All right? Two equations and two unknowns. Kramer's rule says this, that our X variable is going to equal this. It's going to be a top determinant divided by a bottom determinant. Do you remember what a determinant of a 2-by-2 matrix is? We'll look at that real quick. We don't have a whole lot of time, but we'll look at it. For the X, we replace the X coefficients by the numbers over here, C and F, and then we keep our Y coefficients, B and E. For the bottom determinant, we just put the coefficients of our variables, A and D, B and E. And that's what I did up there, all right? What does it mean? What is the determinant of a 2-by-2 matrix? Anybody remember how you do that? Anybody? All right. You take you multiply the downward diagonals together. So in this case, C times the number E, and then you subtract the upward diagonals, B times F. That's how you do a 2-by-2 determinant. Here it would be A times E multiplying the bottom diagonal minus the up diagonal D and B. That's how you do it. So what you get here then, Cassandra, is a number on top and a number on the bottom for your X. And you do a similar thing for the Y. Right? So that's Kramer's rule in 2 minutes. What you end up getting with this, we multiply the bottom minus the top. What I'm going to get here is minus 49 times the cosine of 52. Now I'm going to get a real mess down here at the bottom. I take the downward diagonal, so I'm going to have a minus sine of 40 cosine of 52. That's my downward diagonal. Then minus my upward diagonal, minus sine of 52 cosine of 40 together. Now the deal is, This can be represented as minus, I've got two minuses there, so this can be represented as, I take the minuses out in front, minus sine 40 cosine 52 plus sine 52 cosine of 40. And if you think about this, this gives us a sine, we have a sine identity. The sine of alpha plus beta is equal to the sine of alpha cosine of beta, let's see, plus cosine of alpha sine of beta. All right. So what we really have here, substituting the 40 and the 52 for alpha and beta, is in the denominator I have minus the sine of 40 plus 52, which is minus the sine of 92 degrees. All right. So I basically have this. The magnitude of T5 then is minus 49 cosine of 52 divided by minus the sine of 92 degrees. And the minus signs cancel each other out. We work it out on our calculator, and we come up with an approximation of 30.18. All right? So that's the magnitude of the T5. We do a same kind of thing with Kramer's rule to get the other variable, which is the magnitude of the T3. All right? We don't have time to go through that, but what we get here for the magnitude of the T3 is we end up getting approximately 37.5. All right? Okay. So that was one of the things it was asking. Find the magnitude of each tension. So by solving those two equations, I got the magnitude of the two tensions. Now, the thing is, now I want to put it as a horizontal and a vertical vectors. So basically, I can say this. Okay, that T5, okay, we know its magnitude is 30.18. So I can represent it as a horizontal 30.18 times, oops, not this one, times the cosine of 40 degrees. That's the horizontal component. And then the same magnitude times the sine of 40 degrees. And so what I'll get then with my two components of horizontal and vertical of T5, approximately 23, 19.4. And when I do the same thing with T3, I use my different magnitude for T3, which is 37.5. Now the x1 is in the negative direction, so it's minus 37.5 times the cosine of 52, and then it's 37.5 times the sine of 52. That's our different angle over there. And this comes up to approximately minus 23 and 29.6. What we see here is this, that the horizontal components in this direction of both of the tensions counterbalance each other. One goes in this way of the same magnitude as one going this way. The vertical components add up to 19.4 and 29.6. Those add up to my gravity component downward of 49. So my vertical components also zero each other out. All right. So be prepared. No, never mind. Just wanted to run something that by you because I think maybe one or two of you might have found that a little bit interesting. Certainly, if you're going to go into engineering, you're going to be doing that in a statics course. Absolutely, working with these vectors dividing these vectors up into horizontal and vertical components. So something to look forward to, Nikesha, are you going?
Yeah.
Mm-hmm. Yeah. Yeah, okay. All right, so that wasn't anything new for you then. All right. Okay, I'll see you guys on Friday then. Oh, on determinants?